All right, welcome back. Today we're going to be learning about one of the 5 most important numbers in mathematics. Now, the 5 most important numbers in mathematics are 1, 0, pi, I, and we've learned about all of those numbers, and today we're going to learn about E. Now, E is not just the letter E, but E is a number, and E is a fitting number when we're talking about exponential growth because, or decay for that matter. But E was, how they found that is what they did. They said 1 plus 1 over n to the n power, as n continually increases all the way to positive infinity. And so they said, what if we compounded things? What if we compounded things every year? What if we compounded them every day? What if we compounded them every hour and every minute and every second? And as that number n got bigger and bigger and bigger as you compounded them, it ended up resulting in E, which is very similar to pi in that it never ends. 2.71828 and so on and so forth. And if you find the E button on your calculator, you can, I'll show you where it's at. It's in a couple places, but one of them is right here. Let's quit out of this. One of them is right here, E to the first power, enter, and that's where you can find that number. Okay, so E is going to be a very, very powerful number for you. And what it does is it works on things that are continuously growing or continuously decaying. Remember when we talked about that banana? While you can't tell that banana on the side of the road is continuously growing or the banana on your counter, or the deer on the side of the road that's dead on the side of the road, we'll draw this little deer here. The deer that got hit on the side of the road and his tongue is hanging out and he's on the side of the road, he continuously decays and decays and decays and decays. And that's where our continuous E comes from. Things that happen in nature. That's why we call it the natural base E. When little kids are growing continuously, or your hair grows continuously, those are things that happen in nature, and so that's when we're talking about natural base. We are not talking about things like money in a bank. Those things they're compounded, but they're not continuous growth. All right, let's take a look at example number 1 when we're talking about these things. In example 1, it says e to the 6th times e to the 3rd. This is the same as anything else we had. If I said e to the 6th, I'd be talking about 6 e's all being multiplied together. 1, 2, 3, 4, 5, 6 times 3 e's. And how many e's is that? That's 9 e's. E to the 9th, or e to the 6 plus 3 power. You guys already know that. If I'm looking at this problem here, I have 18 divided by 2, which is 9. 6 e's on the top, 4 e's on the bottom. Well, I can take 4 from the top and 4 from the bottom and end up with e squared. And if I look at this one, I'm going to take my 2 and go whoop to the 4. So now I have 4 squared. And the 2 gets multiplied by the 3x. So it's e to the 6x power. So I end up with 16 e to the 6x power. Change the color real quick. We're going to use a calculator to evaluate these expressions, e to the -2 and e to the 0.3. And how we're going to do that is we're just going to use that same button we just used right here, e to the -2 power, enter, that's what you got, and e to the 0.3 power, and that's what you got. So those are pretty easy to do. You guys go ahead and take a look at that next checkpoint. All right, so when we simplified number 1 there, we had e to the 3rd power, negative 3 plus 6 is to the 3rd. This one, make sure you take the 2 here first, so you had 16 e to the 6th over 8 e to the 5th. Well, 16 divided by 8 is 2, and 6 e's on the top, 5 e's on the bottom, leaves me with 1 e on the top. I'm going to put these into my calculator, and I don't need to bore you with that. If you put that in your calculator, you get 0.18. Hopefully that's what you got. And if you put this one in your calculator, 1.433. Hopefully that's what you got. All right, a function of the form y equals a, whatever the original amount you start with, times e to the rx. I always used to talk about PERT. The initial amount, or your principal, times e to the rate times however much time you have. And so that's called a natural base exponential function. If a is greater than 0, so a is a positive number, and r is greater than 0, so your rate at which something's growing is a bigger number, the function is an exponential growth problem. All right. If a is greater than 0, so it's a positive number again, but r is less than 0, so that's a negative number, now we're talking about things getting decayed. Exponential decay. That's where it's a little bit different than the stuff we were doing before. We'd have 1 plus or 1 minus. Now we have growth and decay. All right. State the domain and the range. All right. Because a is 2, a equals 2 is a positive number, and r is 0.6, that's also a positive number. The function has to be an exponential growth problem. All right. Plot the points. Well, you might plot those points, and you'll end up with the point 0, 2, 0, 2. And then when you put a 1 in there, boy, that's going to be a nasty looking number. You're going to go to your calculator, and you're going to put that in. The one thing you need to know, and we'll do that in just a minute, but your domain, again, is going to be all real numbers, just like it was on the previous lessons, because when we look at the x number, is there anything x can't be? No, I can put negatives and positives. I can put whatever I want in there. It'll all work. But the range on this one will really be determined by whatever your graph looks like. So we're going to take a look at that real quick. Let's hop down here onto my calculator. And go to my y equals menu. And in my y equals, I'm going to have 2 times e to the 0.6 x power. And do a zoom standard. Let's make sure our windows all look the same. Exponential growth, looks like it's that j that we saw before. It's going up here. And so when I flip back over to my graph, it's going to go through here, and it's going to kind of come up and go right through that point and look like a j going up. All right. When we look at the b portion here, that's when you're going to have some h and some k going on. So a lot of changes with that. But in this situation, a is 1. I know you guys are all looking, what's a? Is a 2? Is a? No, a is 1, and that's a positive number. And r is negative 0.35. That's a negative number. The function is an exponential decay. All right. Forgot my c in there. All right. Y equals e to the negative 0.35x. Is you're going to take that original function, you're going to move it left. You're going to move it left 1 unit because of that plus 1 right up here. All right, and you're going to move it down 2 units because of that minus 2. The domain, is there anything I can't put in for x? No, that's going to be all real numbers. You put anything in for x. But the range, because it moved down 2, and it's an exponential decay, but it is, you know, going to go something like, you know, that. It's going to go down. The range ends up being y, but because it went down to greater than -2. And let's graph that on our calculator. Let's take a look at what that looks like. So we're going to go to y equals again, clear this one out. Y equals e to the -0.35 times the quantity x plus 1 quantity and quantity. Now it's important to note what I did here. I had parentheses here 1 and I had parentheses here 2. So I had parentheses here and here to close off both of those parentheses. And then when I add my -2 right here, it's not including that in what it's to the power of. So it's just to that power. So when I graph it, look here when it's going down here. Let me show you that new asymptote. Let's graph the line y equals -2. No. Put it in the wrong spot. Let's go down here. Y equals -2. Let me show you why that's the new asymptote. So as this graph comes across here, that graph goes on there. Now it looks like it touches, but in reality it'll never touch that line. It's an asymptote, so it gets close and it never touches. So that's what your graph is going to look like. And you just, if you'd like on that one, you come over here and you hit table, and you can plot a few points for it. This is for the y1 is what the one you want. All right. Let's take a look at this next page here. You guys are going to do checkpoint 5. Pause the video, take a few moments, graph it, and see if your graph looks like mine. This is the time when you were supposed to pause. Pause now. All right, welcome back. So hopefully when you graphed yours, you just put it in your calculator just like I did, 2e to the 0.7x plus 3. Should have saw something here with an asymptote up there around 3, and that's about all I know from it. So look at there, my asymptote. Let's go down here and just let's just graph 3. My asymptote right there at 3 and going up. So hopefully your graph looked like mine. Okay, so when we're looking at, let's get this calculator out of my way. When we're looking at compounded continuous interest, nobody would ever do this. Nobody would ever pay you money compounded continuously. That doesn't make any sense. But this is that PERT thing we're talking about. You wouldn't go into a bank, put in $10,000, walk out the door, get in your car, go to the drive-thru at the same bank, and say, hey, where's all my money? You wouldn't do that. That doesn't make any sense. No bank would ever do that. That wouldn't be very good business. So you put in $1,000 and you go around to the drive-thru, and they're supposed to give you more than $1,000. Well, they wouldn't be in business very long. So that doesn't work out. This is the principle. R is the annual interest rate. But if you found a bank that will do this for you, great, good for you. I guess standing in line wouldn't be so bad at the bank if you were making money while you were standing in line, right? If you made a little bit more money every moment, then you'd probably want to stand in line a little longer. All right, so let's look at this situation. Here's a scenario. You got $3,500 in an account. It pays 4% annual interest continuously for a year. Well, you got $3,500 times E to the 0.04 for 1 year. So it's just times 1. And let's see how much you would have. We would have 3,500 to the E 0.04 interest, not 0.4, that's 40%. 0.04 would be the right number. $3,642.83. So we'd have $3,642.83. Okay, you can do your own little experiment. Compare that if you had it compounded monthly and see what you get. It would certainly be less money than this. Not a ton less, but it'd be a little less than this. Go ahead and do that last checkpoint on your own, pausing the video right now. All right, welcome back. On this last one, I hope you came up with the same answer I did, $5,833.49. All right. Remember, your equation should have been 4,800. That is very, very bad handwriting. Times e to the 0.065 times 3. And make sure you put parentheses around this part. If you did that correctly in your calculator, you have the right answer. And that is the end of section 7-3. And next we get into logarithms. So that's going to be good stuff. Thanks, folks. Have a great day.